Hey, now that we've learned about continuous functions, we can discuss the intermediate value theorem. It only sounds scary, it's not so bad. Let's jump right into it. And before we state the theorem carefully, let's just describe intuitively what it says. It says that suppose you have some continuous function, like maybe this one right here that I'll call f, and you have some points and I'll call them a and b, so that at a, here's some point f of a, and at b, you get the function value f of b right there. It says that because this function is continuous, and it hits this value on the y-axis and this value on the y-axis, well, somewhere between a and b, it has to hit every single one of these other values on the y-axis. In other words, it can't possibly skip over any y values. That's what it means to be continuous. Here it is carefully, the intermediate value theorem. Suppose f is a continuous function on the closed interval from a to b. That's the interval from a to b that includes the endpoints a and b. And suppose that f of a is not equal to f of b. In other words, the function has different values at a and b. Then take any number n between those two values, f of a and f of b, and somewhere there's an x value that here I'm calling c between the a and the b, such that when you plug it into the function, you get that value n. This only works because the function is continuous. If the function wasn't continuous, it could skip over values wherever it wanted to. But for continuous functions, this always holds. Let's do an example. Here's a function f. F of x is x cubed plus x minus 5. It's a polynomial function, so it's continuous everywhere. And you can notice that f of 1 is negative 3. It's 1 cubed plus 1. That's 2 minus 5, which is negative 3. And f of 2 is 5. F of 2 is 2 cubed, which is 8, plus 2 is 10, minus 5 is equal to 5. And so, by the intermediate value theorem, this function f has an x-intercept, a 0, somewhere between 1 and 2. I mean, here's the picture. At 1, the function has the value negative 3. At 2, the function has the value 5. And so, by the intermediate value theorem, because it's continuous, there's no way it can get from negative 3 to 5 without somewhere crossing through 0. Don't know where, but, it looks something like that. So, whatever that point is. It might look nothing like that whatsoever. All the intermediate value theorem says is that somewhere between 1 and 2, this function has to attain the value 0, has to obtain the function value 0. It has to attain every value between negative 3 and 5. Is there some point between 1 and 2 where this function is equal to pi? Absolutely. How do you know? Because pi is over here somewhere. And so there is some place, some value between 1 and 2 where this function gives you the value pi. We'll do one more fun little silly trick with the intermediate value theorem, and then we'll call it done. We'll prove that there's a number that's exactly 1 less than its cube. If you call the number x, then what we're saying is that x is equal to its cube minus 1, so x is equal to x cubed minus 1. Or subtracting x from both sides, that tells us that x cubed minus x minus 1 is equal to 0. So we're trying to show that there's some number x that satisfies that equation. Well, consider the function f of x equals x cubed minus x minus 1, a polynomial function, so it's continuous everywhere. And observe that f of 0 is negative 1, and f of 2 is equal to 5. And so by the intermediate value theorem, somewhere between 0 and 2, there's an x value that makes this function equal to 0. And so somewhere between 0 and 2, there is a value that is exactly 1 less than its cube by the intermediate value theorem. Okay, that was the intermediate value theorem. Pretty straightforward. There is no corresponding homework, but we'll need it later on in the semester. Okay, see you soon.